here's what we have coming up. So what we'll do today, we'll take part of the class to tuck in some new stuff. On Wednesday, we'll take part of the class to do some new stuff. The rest of today and the rest of Wednesday we'll have open for labs. And then I'm going to leave Friday and Monday open to get caught up on any lab stuff, homework stuff, take home test stuff, any of that kind of bit. So hopefully that gives you plenty of time to get everything done. And then we'll look to do our test next Wednesday. So just got a couple things to add in. The first thing we'll cover today really isn't anything new. It's just kind of stuff we've done before but applied to circuits with resistors in them. This part here is new. This is something that we haven't seen before, so we'll get that today. And then this is kind of combining some things that we've done. So let's take a look at this problem here. Hopefully this kind of a thing looks sort of familiar, except we're doing this with capacitors. There'll be problems related to resistors in circuits that are going to be very similar to what we saw with those capacitor problems. In this case, I've got a circuit with a bunch of resistors in it. I've got some voltage between the two terminals. So that's going to send some current into here. The current gets split up into different branches and then ends up back to our power source. Some different questions that could be asked here is, all right, whatever current is running through here, how does it get split up in here? How much current is running through this resistor, this one, this one? Probably the furthest along we can take this problem is to ask how much power is dissipated across each of the resistors. But similar to what we saw with capacitors, where with capacitors we looked at how much potential energy was stored, and as long as we had any two of the Q, V, and C, we could figure out the potential energy stored in that capacitor. Here it's going to be the same type of thing. If I want to know how much power is dissipated across a resistor, as long as I know any two of V, I, and R, I can plug it in here and figure out how much power is dissipated. So let's do it this way for this particular problem. Let's see if we can figure out how much current is running through the whole circuit, and then how does that current get split up? In other words, how much current is going to pop out of this positive terminal here, and once it pops out of here and hits all this stuff, how is it getting split up through this circuit? Or another way you'll hear that asked is, how much current is running through each resistor? So just like we did with capacitors, the first thing we'll do is go step by step and turn this into one final equivalent resistor. And hopefully by now you're starting to see when things are in series, when things are in parallel. What you're looking for is when they're in parallel, a current comes and hits a junction, splits, some of it goes through one, some of it goes through other, and nothing else happens before it comes back together again. Those would be in parallel. Notice that this guy is in series with this set, because whatever current goes through here has to end up going through this piece, and then comes back again. So with that, we can start to identify series and parallel combinations, turn them into equivalent resistors. So let's go step by step. You're all okay with that, right? Those two are in parallel. The only thing we have to remember is when we get equivalent resistances, this is backwards of how we did it with capacitors. So I'm just going to redraw a picture here. And by the way, notice that these units here on resistance are ohms. So I don't do a very good job of drawing this. It's a Greek letter omega. It looks like that. So to turn this guy into an equivalent resistor, remember when they're parallel with resistors, that's when we do that 1 over stuff. So 1 over 4 plus 1 over 12. And then remember, hopefully you're good at this now, I've got to flip that answer over to get the actual equivalent resistance. These two are then in series. If they're in series, that's when with resistors we just add them up. And then these are in parallel. And we finally get to, our final equivalent resistor. and you end up with a final equivalent resistance. If we need to know information about the whole circuit, we can use what we find for this final equivalent resistor. That represents our entire circuit. So what we have here is an equivalent resistance of 6 ohms. Since this is the only thing between our two terminals now, I know that the potential difference across that last resistor is whatever I had there for the whole circuit. So I know V is, for this example, 12 volts. I can figure out then the total current going through my whole circuit. That's just V over R from Ohm's law. And that tells me that there's 2 amps going through that whole circuit. In other words, if I go back here, what's this battery spitting out here? I've got 2 amps of current coming into all this stuff that it's going to hit. If I want to know how that's split up, how much is going through each resistor, what we're going to do is go backwards through this, like we did with capacitors, where we're going to take a look backwards and see, of course that's right in the way, as we step back in our sequence here, where this equivalent resistor came from, and that's going to give us some information that's going to be useful. Notice this equivalent resistor came from these 2 guys. That came from 2 that were in parallel. Just like we had with capacitors, when things are in parallel, their V's are the same. What that means is whatever V we had here, it's the same for this one and for this one. So that tells me, let me try to draw it here, that for this bottom one, sorry, rather than move things around here, I know the resistance was 8 ohms. I know the potential difference across that was 12 volts. And from that I can figure out how much current went through there. For this one, let's see, its resistance was 24 ohms, the voltage was the same as I had there, 12 volts, and that tells me then that the current going through there was half an amp. And notice this one here is actually one of our original resistors. So here is the current going through one of our original resistors. In fact, notice if we stop right here, at this point, I've got 2 amps coming into this. 1.5 went to the bottom branch, half went to the top branch. Comes back together again, there's my 2 amps going back. So we've got one of our original resistors taken care of. This one here, though, wasn't one of our originals. That's an equivalent resistor. So let's go back another step and see where did that one come from. Oh, it's from these 2 guys. They were in series. And just like with capacitors, when things are in series, with capacitors we said the Q's were the same. With resistors, it's the flowing Q's. Now our Q's, our charges are moving. In other words, the currents are the same. So whatever current we found for this guy, that 1.5 amps, that's the same here and here. So this guy here was one of our originals. So we're done with him. This one, though, we'll figure out a few things there. Again, sorry for having to move things around the board on you. So I know the resistance is 3 ohms. I know the current, same as we had over there, 1.5 amps, which means I can find the voltage. Just multiply those 2 together, and I get 4.5 volts. So I know everything I need to know about that. That was an equivalent resistor. Let's take another step back. That one came from these 2. And here's where circling them, putting a little arrow over to them helps you remember where things come from. That guy, let's go backwards, came from these 2. They were in parallel. That means V's are the same. Whatever V I just found there, that's the same here and here. Now we can finish these guys off. So this has a resistance of 12 ohms, has a voltage of 4.5 volts, which means a current of 4.5 divided by 12. Oops. That's one of our originals, and then this one here. Four ohms. Voltage 4.5 volts. And current then comes out EE 1.125 amps. And so now we know how our current got split up through all these different resistors. Again, if we wanted power instead, all we'd have to do is take any V, I, and R and just plug it into these. We can get power out of that too. Any question on how to do these kind of problems? With a little practice, these aren't too bad to do. And again, we've done them with capacitors. This is not much different other than remembering in series, add them up, in parallel, do the inverse and stuff. So, any other questions on those? Okay, so now the new stuff. Put a different circuit up here. So let's say we've got a circuit that looks like this. And let's put some numbers on here. And the units on these resistors are going to be ohms. I'm going to leave them off just so it makes a little bit cleaner picture. So let's say we've got a circuit like that. And we want to know, hey, how much current is going through each of the resistors. So far it sounds similar to what we just did. Why can't we do what we just did to that? Notice the technique we just used. We looked for resistors in series, resistors in parallel. We turned them all into one final equivalent resistor, and then we just went backwards and figured things out. Why can't we do that with this one?
Two power sources.
Mm-hmm. We don't have a nice set of resistors in series, resistors in parallel. So let's look at these two. Oh, there's two resistors. If that wasn't there, I'd buy that they're in parallel. But the problem is, let's say I send a current into this branch, it goes like that. There it is going through our two resistors. But oops, I've got something else that's going to happen before that current gets back together again. So those are not in parallel with each other. So I've got that guy in the way. When you run into this, we've got a whole new technique that we're going to have to deal with. How many different currents are in that circuit, by the way? See if you recognize that yet. I don't think I'm seeing another answer yet. So, you're okay with that's in series. Whatever current went through this has to go through this. As long as we don't have any junctions, that's the same current, right? So let's use that to take a look at this picture. As long as I'm over here, There's no junctions anywhere here. This is all the same current there. There's some junctions. As long as I'm over here, that's all one current. And as long as I'm here, that's one current. So how many total do we have? There's one over on the left branch, one on the right branch, and one down the middle, up or down the middle. So I've got 3 different currents in a circuit like this. If I have 3 unknowns, how many equations are we going to need to figure out those 3 unknowns? So 3 unknowns, how many equations? 3. Same number of equations as unknowns. So we're going to come up with a technique that's going to give us 3 equations for 3 unknowns for a circuit like this. I might have asked this before. Any of you know how to use matrices? Oh, it's a shame. These are super, super easy if you know how to use matrices.
Well, I mean,
It rings a bell.
If you can do it, I'm fine with that. Just let me know that's what you did on the tests. But otherwise, it looks like we're going to do it the longer way. But you all know how to do this. We'll take a look here and see.
I know this isn't a math class, but how would you use matrices for this?
I'll show you. It's designed for matrices. The good news for you guys, since I figure you don't know matrices, we're going to only do simple problems where you're only going to have 3 unknowns. If you know how to use matrices, you can have as complicated a circuit as you want. If it's 10 unknowns, matrices can solve 10 equations, 10 unknowns without a problem. For you, it's a little bit longer because it's a lot of algebra. So as long as you get this concept, we're good.
Can you do the currents one more time? I just want to make sure.
Yep. We don't know the directions yet, but there's one current in this branch because there's nowhere else for it to go. Whatever current goes through this has to go through that.
Okay.
There's a separate current in this branch. And there's another current up and down the middle. Up or down, we don't know that. So the way we're going to do this is use what are called Kirchhoff's rules. And what Kirchhoff's rules say in words, then we'll put them into use. So in words, maybe not quite as useful, but we'll see if where this makes sense. One of the rules says that whatever current comes into a junction had better come back out of that junction. So let's say I've got a junction right here and I send a current this way and my current hits this. Whatever I sent in, it better add up to whatever came out. I shouldn't somehow magically gain or lose current just because I hit a junction. So again, in words, Kirchhoff's junction rule says whatever current goes into a junction comes out of a junction. Kirchhoff's loop rule says this, that if I add up potential changes around a closed loop, notice I'm crossing a battery here, so I'm going to have a potential change. When I cross a resistor, I'll have a potential change. As long as I stay on a closed loop and I add up the potential changes across all these circuit elements. So let's say I start right here, I cross one here, cross another one here, and let's go down the middle then, cross one here, and I'm back to my starting spot. What should those potential changes add up to? They better add up to 0. In other words, I shouldn't be able to magically gain potential just by going round and around and around and around. In some places I'm going to be gaining potential, but then I'm going to lose it somewhere else, so that I'm back to my original potential. In other words, I add up, I'll add up to 0 on any closed loop.
So in closed loop, whatever it starts with, by the time it gets back around, it's going to be the same as what it started.
It better be. I shouldn't somehow magically gain potential or lose potential. As long as I'm on a closed loop. So, here's how we're going to set this up. And what's maybe confusing at first, but actually really nice, is you've got total freedom in how you want to set up this problem. And what I would recommend is making a little sketch that shows exactly what you have in mind. And what I mean by that is I'm just gonna draw a simple little sketch here to represent my circuit. And what we're gonna do is pick a junction to use, label some currents, 1, 2, and 3, and then pick directions around loops that we want to go to add up those potential changes. And you are free to do it however you want, but once you get it set up, stick with your convention all the way till the very end of the problem. So let's see what all that means. Notice that I've got 2 different junctions I can use, one at the bottom, one at the top. You can use either one, it doesn't matter. Pick one. For our purposes, let's do this. Let's pick that junction right there. I've got 3 different currents. Let's label them 1, 2, and 3. Doesn't matter which one you call which. Let's pick some directions for the currents. Doesn't even matter what direction you pick. You don't have to guess which way it really is. Just pick something. Again, for practice, we'll do it this way. Let's say current 1 is the one that goes in the middle, and let's guess that it's going to go up. Current 2, we'll say that's in the left branch, and let's guess it's going to go right into that junction. Current 3, let's do it this way. Maybe they go that way, maybe they don't, doesn't matter. Our answers in the end will give us the right directions, but pick something. How many different possible closed loops do we have? There's actually 3. I've got one around this left side. I've got another around the right side. If I want, I can even go all the way around the outside. Pick any 2 of them, doesn't matter. Just pick 2. Clockwise or counterclockwise, doesn't matter, pick something. But again, it helps to have a sketch so that you remember what you picked and remember what your conventions were. So let's try it this way. Let's do the right-hand side as our first one, and let's go around that way. So that's going to be loop 1. And then our second loop, let's go on this side like that. And we'll go clockwise. Again, it doesn't matter, just pick something. Then we can set up our little Kirchhoff's rules equations. What you want to do here is 1 junction equation, 2 loop equations. So for our junction equation, super easy. Here's the easiest way to do it without even thinking. An equal sign there. Whatever current goes into the junction, it's on the left. Whatever current comes out of the junction, it's on the right. Notice how this is set up. I've got currents 1 and 2 coming in. And current 3 is coming out. In fact, you could have even done this. Now, can that possibly be correct in the end? There's no way, because all the currents come in, and it says nothing's coming out. Doesn't matter, that'll still work. I could still write a junction rule. There's what came in, there's what came out, and the problem's still gonna work. I probably wouldn't do that, because I know it can't be right, but it doesn't matter. I'll show you when we get to the end why I say none of this matters, how you set it up. As long as you set up something and stick with it the whole rest of the way. Now let's do these loop rules. So loop 1. So what we're going to do is, here's our circuit, and we've got some elements here. We're going to start somewhere, go in a closed loop, and add up our potential changes. I did print this out, just so you have it in front of you for today, of the conventions that we're going to use to count up these potential changes. So this is on the cover sheet that you'll have for the test, but just as a reminder of where this is. So this would be on the back side. So on your test, if you printed the front side, back side. If you look in the upper left of this part, you'll see the conventions that we're going to use to count up our potential changes. And what you'll see is the thing I have already written up on the board there in blue. And let's see what that means, then we'll run through this example to see how that actually works. So what you want to do is we picked some directions already for the currents. So we know what directions we guess the currents were going to go through those resistors. What we're going to do is compare, and the batteries I should say, so both. What we're going to do is compare that to how we're going through it as we're walking around the loop that we chose in the direction that we chose. If, as we cross a resistor, so we're going to be starting somewhere, we're going to be walking along like this and passing through different things. If, as we're going around the loop, we happen to go the exact same direction as the current goes through that we had chosen, that the current goes through the resistor, we're going to count that as a potential drop of that current times that resistance. And notice from Ohm's law, you can look at it either that way or that way. For the resistors, we're going to look at the IR part. So if we go the same way the current goes, we're going to have a potential drop of that I times that R. If we happen to go backwards against the current to a resistor, we're going to get a potential change that's a plus IR. When we run into a battery or power source, if, as we're going around the loop, we go through the battery, I guess in my mind, the normal way, we go into the negative, out the positive, we're going to gain whatever potential that battery had. If we go through a battery the wrong way, so we're going around our loop, we go into the positive, out the negative, we're going to count that as a potential drop of whatever that battery had. Okay? That's what that stuff says on that upper left corner there. So let's see what that means. So let's start right here and go clockwise and count up our potential changes. So I'm going to start here, nothing, nothing, nothing. Oops, I hit a battery and I went this way through it. Is that a plus or minus 10 volts? That's a plus 10. I'm going to leave the units off again, keep this over here. All right, then I go through a resistor. Notice I'm going the same way as the current we picked. And it's I1. So we're going to lose 6 I1s. That resistance times that current. If it helps, once you set this up, if you want to put them on here, that's fine too. However you can see this best. Come up here, turn this way, nothing, 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 then I come down like that, and I cross the resistor. I'm going the same way as I3. So I'm going to lose another 2 I3s. That's I3 over in this branch. Nothing, 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 I'm back to my starting point. So I've accounted for the 3 circuit elements in that loop. What do they have to add up to? 0. All those changes are going to add up to 0. Let's do our second loop. Let's start right here. Again, you can start wherever you want. And we're going to go clockwise. So I come down like this. First thing I hit is a resistor. I'm now going against the current. So that's a plus. There's my resistance. Here was the current that I was fighting against. Come through a battery. I'm going the wrong way through it. So I lose that much. Come down here, come across this guy. Let's see, that whole branch, that's I2. And again, if this helps to do this, that's fine. That's I2 the whole way like this. As I come across, I'm going the same way as I2. So I'm going to lose 4 I2s across that guy. Come up to here, I hit a battery. I'm going the right way through a battery, the normal way through. So I'm going to gain 14. And keep going, complete that circuit or that closed loop, and I'm back to my starting point. And so those have to add up to 0. notice we now have 1, 2, 3 equations. And you guys know how to do 3 equations, 3 unknowns, right? Here's what I would do then, since I got those looks from you guys. You should see what this looks like from my side. It wasn't even the blank stares this time. It was more like horrified looks. Here's a good way to do this. Let's make these look prettier before we start to do any more. What do I mean by that? I've got I1s, I2s, I3s scattered throughout there. Let's write them kind of in order, and any constants let's put over on the other side of the equal sign. So let's rewrite this equation as minus 6I1 minus 2I3s is equal to, let's put the 10 over to the other side. Same thing here, I've got 6I1s, let's see, minus 4I2s, and that's equal to what? What did I miss here? Oh, that's what I missed, sorry. I gotta draw my picture right. Sorry about that. I drew it wrong. This will work better, sorry. I accidentally drew that one wrong. So it's flipped over this way. So we actually, when we came around, went the wrong way through it, so it was a minus 14. So I've got a minus 24 total on this side, that turns that into a plus 24 on the other side. These are our 3 equations. And here's the best way to do these, for those of you that aren't as familiar with this. And there are different ways to solve multiple equations, multiple unknowns, but this is probably the easiest way. I've got I1s, I2s, I3s. I'm going to do something to eliminate one of them as a first step. However, there is one I don't want to get rid of. And what you want to look at is in your 2 loop equations, at least with the loops we picked, one of those currents is going to be in both of them. Don't get rid of that one. In fact, I would even do this. Which one are we going to keep? Got I1 in both of them. I want to make sure I don't get rid of that. Get rid of either I2 or I3, but it's going to complicate things if I try and get rid of the thing that's in both of them. Part of the reason I prefer to set it up like this, even though you don't have to, is it makes it really easy now to substitute for I3. Because notice wherever I've got an I3 in these equations, it's the same as this. So typically the first step is to put your junction into one of those loops. Again, you can do it other ways, but the easiest for me is to go, okay, let's put it into our second equation. There's I3 right here. I3 is the same thing as I1 plus I2. Or, oops. Altogether now I've got a minus 8 I1s, let's see, minus 2 I2s is minus 10. So again, usually the easiest thing to do first, take that junction rule, use it to substitute for anything except the one that's the same in both. And for me it's easiest just to do the I3. So let's see where we're at so far. I'm going to try and go like this so you can see these. So that was from equation 2. Let me put equation 3 right by it. Now, how many equations, how many unknowns do we have? Now we're to 2 equations, 2 unknowns. Does that look like something you can solve? That should start to look more familiar. And again, there are different ways to do this. The easiest way, because the numbers aren't always going to be as pretty as this particular example, is to decide which one of these you want to solve for. We could do one or the other. And then let's do this one kind of the easy way. Let's say I want to find I1 and get rid of I2. How can I get rid of I2? So I'm bound down to 1 equation, 1 unknown.
Set the equation equal to I2
That's the hard way to do it, but you could.
and substitute.
It's a whole lot easier if I multiplied this thing by -4. I'm sorry, by -2. Then, let's see what we get here. Let's see, I need that to, why do I need that to be a minus? Because I'm going to make this look all nice and pretty. You'll see. Plus 4I2s is equal to plus 20. So I have to do that to every piece there. Here's this one, 6I1s minus 4I2s. Now what? What do I do with that? I just add them. Because what happens when I add those? They cancel. I end up with 22 I1s. That's equal to 44. Now I've got 1 equation, 1 unknown. There's I1. What if instead, I was back here, and instead I decided, I don't want to solve for I1 first, I want to solve for I2 first. What's the easy way to do that? Without even having to think much. If I want to get rid of the I2s, I'm sorry, the I1s. This is easier to do than to say in words. Multiply the top by that guy, and the bottom by that guy. You don't even have to worry about common denominators or any of that, just whatever it is. Multiply this one by 6, this one by 8. Check the signs. If they're not opposite signs, make one of those out here negative. And I can get rid of that one instead. As long as I do that to every single term in there. So we did it this way. I ended up with one of my currents. Now what? I got one of the 3. I can stick that back into any of these equations I have. Let's go back all the way to this one here. We're going to go this way. So I know what I1 is now. I stick I1 in there. Now I've got back to 1 equation, 1 unknown. What's up with the negative?
You guys do it right now.
That tells me, back here when I guessed at the direction of I2, I guessed wrong. The real direction is opposite of what I picked. But stick with your convention till the very end of the problem. Because now we need to find I3. Here's an easy way to do it right here. But don't get rid of that negative yet. Keep that all the way to the end. Because everything we set up here was with that wrong direction, so let's stick with that. In other words, when I add these up, I1 was a plus 2 amps. This was a minus 3 amps. And that says that I3 is this. So what does that mean? I3 is 1 amp. But we guessed that one wrong too. Oh well. So then to finish this off, just draw one last little sketch to show the real directions. So those were our conventions. Here's the real story. Is I1's this way. I2 was actually this way. And I3 was actually this way. And let's see, does that make sense? Sure enough, here's 1 amp coming in, 2 amps coming in. So that means grand total of 3 amps came in, here's our 3 amps coming out. So yeah, that is all consistent. So that's why I say it doesn't matter what you pick. Your answers in the end will tell you what the directions really are. But don't get rid of those until you're done at the very, very end, have all your currents, then flip the directions. These are actually really easy to practice too, because you have such a variety of ways you can set the problems up. You can do the same problem different ways just to see if you can get to the same answer if you need more practice. I'm going to do one more here. I'm going to go through a little bit faster this time. And this one's out of your book, but we'll do it a little bit differently than your book set it up, just so you can see another way to do it. Then I'm going to have you guys try one, and then the rest of the time we'll leave open to lab activities where you guys can see. So one more practice up here, one more for you guys. We'll see how we do. So this is actually example 21.5 on page 751 of your book. So here's the circuit. By the way, again, all we're going to do are 2-loop circuits, which means your only options are either your loops are this way or they're this way. So once you get a way to do those two, that's about it. The reason I say if you know matrices, these are so easy to do. That's a matrix problem, for those that know that. You just line up the 1s, 2s, and 3s and constants over on the other side. And if you had more of them, it's just a bigger matrix. But matrices are really good at solving those kinds of problems. Since you don't know how to do that, probably, we don't have to worry about 4, 5, 6, 8, 10 equations. If you know how to do the 3 equations, 3 unknowns, in concept, you know how to do the rest of them. So we'll stick with one of these 2 options. two loop circuits either this way or this way. So let's do one the other way, just so you see how that works. So here's what your book did. So this is not how we're going to do it, but just so you know. Your book did this, which is just fine. They used this junction. They said I1 was this way, I2 was this way, and I3 was this way. That's the conventions they set up to solve the problem. They found this. So what does that mean? Just means two of them they guessed right. I1 really was this way. I3 really was this way. But I2 was actually this way. Let's try this problem, see if we can come up with what they got, but let's try a little different convention. Let's try for our version this. Let's use this junction. Let's call I1 this way, I2 this way, and I3 this way. Again, you're free to set these up however you want. Let's do loop 1 like this, and loop 2 like this. You know, pick whatever you want, whichever way you want to go. Let's try that. So, our junction rule says, the way we set it up, I1 and I2 came in, I3 came out. There's our junction. Loop 1. I'm going to add some things here. Just as a reminder of what we did. It's I1, becomes I3, and I2 is this way. Sorry about this, I keep missing stuff. There's one more in here. Sorry, there's one more in this little branch right here, just to match up what they had. Okay, sorry about that. All right, so let's start adding things up. So let's start right here and come down this way. So I'm going through a resistor, the same direction the current's going. So I'm going to lose 1.5 I3s. Next thing I get is a battery. Oops, another resistor, sorry. So I got another 0.5 I3s that I lost. Then I hit that battery going the wrong way through it. So that's minus 45 more. Then come around like this. Oops, now I've got a different current going the same way as I1. So I lose another 6 I1s. Then I'm back to my starting point, so that ends up to 0. Let's clean that up a little bit. I've got minus 6 I1s. Altogether, I've got minus 2 I3s. And that 45 gets stuck to the other side. The equal sign. Here's my second equation. My junction's my first equation. Loop 2. Let's start. Let's start right here and go around. So I go backwards against my current, so I gain 6 I1s. let's see, now I'm in the upper branch, so we're talking I2s, I'm going the same way, so it's minus 2.5 I2s. Going the normal way through the battery, so plus 18 more, minus another 0.5 I2s, and then I'm back to my starting point. Cleaning that up a little bit, I've got, let's see, 6 I1s minus 3 I2s, and 18 goes to the other side, equal sign. And so there's my third equation. So I've got my three equations, three unknowns. The thing that's the same in both of my loops is I1. So I'm going to remind myself to keep the I1s, don't get rid of that. So I'm going to use my junction equation, put that into one of the other two. Right now it's set up to get rid of the I3 pretty easily, so I'm going to put that into my second equation. So it's minus 6 I1s minus 2 I1 plus I2s is equal to 45. Simplify that a little bit, so altogether I've got minus 8 I1s minus 2 I2s. Let's take our other loop equation, put it underneath this one. Let's get rid of, and again, we could get rid of either of them. Let's get rid of the I2s. So how do I get rid of I2 if these are my two equations? Without having to think a whole lot. Multiply the top by 3, the bottom by 2. These are the same side, so one of them is going to have to be negative, just so I get opposite signs there. So let's do it this way. Multiply this one by 3, this one by 2. Just to get opposite signs, let's make the bottom one here. Just make sure you do that to every term, and we'll be good. So that should be minus 24 I1s minus 6 I2s is equal to 135. And the bottom one, I've got minus 12 I1s plus 6 I2s is equal to plus 36. If I add those up, my I2s go away. Get minus 36 I1s is equal to 171. So I1 is then 171 over minus 36, which is minus 4.75 amps for I1. Which, by the way, notice, that's what they had. Ours is backwards, sure enough. So we got exactly what they had before. Once we have that, we can stick it back into any of these equations. Let's actually stick it back into this one. So 6I1 minus 3I2s is equal to minus 18. Or 6 times, keep the negative in there. We're not going to change any of that till the very, very end of the problem. Minus 3I2s is equal to minus 18. Let's see, this is minus 28.5 minus 3I2s. Minus 18 minus 3I2s is equal to a plus 10.5, or I2 is equal to 10.5 over minus 3, which comes out to be minus 3.5 amps. That's I2. And then I3, we'll just stick it right into a junction equation. Again, leave those negatives in there. So minus 4.75 minus 3.5 gives me minus 8.25 amps. for I3. And now we can finish things off by making a little sketch to show the actual directions. And unfortunately, we guessed wrong on every single one, but it doesn't matter because our answers tell us that I1 was actually opposite of what we picked. I2 was opposite of what we picked. And I3 was opposite of what we picked. And notice that matches up to exactly what they have. Same numbers, same directions in the end. So, now your turn.
On the initial diagram, how come you have like for the batteries, the plus doesn't go into the minus?
Here's the positive terminal, here's the negative terminal.
Yeah.
We can set them up in a circuit any way we want. Are you asking why are they set up this way?
Yeah, like when it flows through, doesn't it have to go positive and negative? It doesn't matter.
Not when there's multiple ones. That's why we have to do this and figure out ultimately what direction did we end up. So, in other words, well actually this should make sense that it better go that way. But here and here, it depends on how much voltage these batteries have and what our resistors are as far as are we going this way or this way in a net effect. So no, you don't have to have the batteries all lined up. And there are reasons in real circuits to do it that way. So here's one for you guys to practice. And as soon as you get this one done, then the rest of the time today is for whatever you guys need. You want to get back into lab activities? And in this case, just so we're all doing the same thing to figure it out, I did pick the conventions for you right here. But again, you could do it any way you want. If you want to practice this problem and pick different directions or different numbers or different junctions, you can do this thing a bunch of different ways. But the answer should all end up the same.